happy to have Warren Lee tell us about progress towards the BKL proposal.
Thank you very much to the organizers. I've been here a couple of weeks now, and I really like my stay at the Fields Institute and being in Toronto. So I'll talk to you today about the BKL proposal, which is kind of a physics heuristic about space-like singularities in GR. So I think today, at least the remainder of today, will be very themed in that sense. So because I don't want to write the names down later, so BKL stands for three Russian physicists. So this is Belinsky, Kalatnikov, and Lifshitz. So whenever I write those initials, we'll know what that means. Okay, so let's get started. So I'm going to today just consider the Einstein vacuum equations. Which everyone knows is just for a four-manifold and a Lorentzian metric, and it just says that the Ricci tensor of the metric is 0, and I'll probably call this EV. So as I said, I'm going to be talking about singularity. So let me just recall the singularity theorems. So we have singularity theorems of Penrose and Hawking. So let me write down the Hawking theorem. 67. And this says that if we have initial data for the Einstein vacuum equation, so I'll just hope that everyone knows what this is. So this is a three-manifold together with a Riemannian metric on the manifold and a two-tensor that represents the second fundamental form. So let this be initial data. For the Einstein equations, such that the trace of the second fundamental form with respect to H is strictly positive. Okay. Then what the theorem says is that the maximal globally hyperbolic development of this initial data is, well, I want to say singular, but what they really show is that it's geodesically incomplete, or let me say past time-like geodesically. So okay, in my talk, all my singularities will be to the past. In reality, the Einstein equations, of course, have kind of time reflection symmetry, so it doesn't really matter. Okay, so let me use this board. So kind of the main question is, okay, this theorem is proved very softly, using very, very little information about the Einstein equations in reality. And the main kind of question is, what does this singularity look like? And I'll write singularity in quotation marks just to emphasize that we don't really know formation of singularity in the sense of something blowing up, just incompleteness. Okay. So one way we could answer this question is we first look at some model examples. So let me just write down some model singularities. And the first of which is going to be the so-called Kasner solution. Kasner family, let me say. So this was written down in, I think, 1921. And here we have M, which is going to be positive reals. So that's going to be time across, say, the say R3. And the metric here is the following, so minus dt squared plus this metric, so dx squared. Okay, so what are these numbers? So P1, P2, and P3 here are just real numbers, and this solves the Einstein vacuum equations if following two algebraic relations hold. So the sum of the PIs and the sum of the PIs squared is equal to 4. Okay, so it's a little bit like Minkowski space. Actually, if you ignore the T, and look at fixed t, this actually is just a rescaling of Euclidean, the Euclidean metric. But importantly, we have these weights in t, and we really see there's some kind of degeneration towards t goes to 0. So let me make some more comments on that. So remarks. So firstly, so if we think about what these algebraic relationships say, I've written family here, and really it's a one-parameter family of such solutions, because we have kind of 3 parameters here, but they're constrained by 2 equations. So one-parameter family. And actually, if you think about what these PIs satisfy, this is the intersection of like a plane with a sphere. So it's really parameterized by a circle. So let me say in parentheses, Käsner circle. Circle like this. And another thing to notice is, just for fun, is that if you have 3 real numbers that satisfy these relations, you can check that exactly one of these must be negative, or maybe I should say non-positive. So exactly one PI is non-positive. Okay. Next, what I want to say is that this does, in fact, work with the Hawking theorem. So in particular, if I consider the constant time hypersurface, say sigma tau, which is just tau xyz, xyz 3, then you can check that the kind of trace of the second fundamental form on the sigma tau is exactly 1 over tau. Okay, so in particular, but as long as tau is positive, this thing is bounded strictly away from 0. So Hawking theorem applies. And moreover, I really want to say this is an example of a singularity. And one way you can do this is you can check that the curvature invariant, which is the Kretschmann scalar, which remember is just the complete contraction of the Riemann tensor, is scales as tau, t to the -4. So it really does blow up as t goes to 0. And that's why we call it an example. Well, that's why I call it a model singularity. Okay. Good. So that's our first example, but life is not that simple, and we really have to think about more complicated things. So let me now discuss another family, which is, well, maybe not another family, another more general class of spacetimes, which looks at, I mean, has some similarities to Käsner, but will look much more complicated somehow. And this will be the Bianchi class. Okay, so here M will again be positive reals across now a Lie group. Okay, and on this Lie group, I'm going to put a basis of right invariant 1 forms. Maybe omega 1, omega 2, omega 3. Okay. And I'll write down a metric, which is maybe slightly similar to the one there, so minus dt squared. And then again, instead of t to a power, I'm just going to have some function of t. And then these one forms. Okay. Okay. So like Käsner, this is an example of a spatially homogeneous solution, right? It still admits, okay, maybe I didn't say this up here. So I should have said that up here, this, so d by dx, d by dy, and d by dz, which that letter looks terrible, are all killing fields for this metric. And actually just over here, if you kind of look at the kind of dual basis of vector fields, they also are killing for this metric, okay? So this is spatially homogeneous. And okay, because it's spatially homogeneous, really the only kind of degrees of freedom are these kind of this kind of dependence on time. Okay, so you can really see that the Einstein vacuum equations reduce to ODEs for these AI. Okay. So in reality, what you actually get is a 5-dimensional dynamical system. Maybe in words, this is because we get 3 second-order equations for the AI, but we also get a constraint equation. Okay, good. So before we move on to thinking about the Einstein equations as any kind of PDE, let me first discuss a little bit just about this system of ODEs. So let me say in the kind of general Bianchi. So for those who know, this would be Bianchi 8 or Bianchi 9, where maybe G3 is something like SU2, something like that. What you have is that the fixed, firstly, you know that the fixed points of the system corresponds exactly to that circle, corresponds to the Kasner circle. Okay, so we have a circle here. And okay, if we're just studying a dynamical system, the next thing to do once you have fixed points is to kind of study maybe the stability of these fixed points. Okay, so what you can say is that each of these is unstable. Let's say unstable with respect to time going to 0, because that's the direction we're interested in. Okay, and in fact, it has the linearization has kind of 1 unstable eigenvalue. Okay, and that means what we can do is we can study what's called the unstable manifold of each of these points, which is just a 1-dimensional object. And then, okay, let me write that down. So the unstable manifold, let me call this point P, say P. It actually connects to another point on the circle. So maybe I should have drawn the picture first. It's just simply that if you shoot out this unstable direction from P, you'll hit another point on the circle there. Okay. So this is called a heteroclinic orbit. Okay. And that's good. So, okay, maybe in this talk later on, I'll refer to such thing as the bounce. And okay, let me just say that kind of, so this is a very specific orbit of the dynamical system. What you could really care about is maybe what happens if I start with data over here and I kind of evolve. And what you really expect is that, you know, at some point you'll get close to this circle and then you will follow this unstable direction. But then this point also has an unstable direction of its own. It also shoots out that way. And then you'll keep following these things. Okay, so let me just say that we expect kind of generic orbits to, say, converge to, let's say, a cascade of such bounces. And okay, actually, even this map taking this point to this point on its by itself is chaotic in the sense of a discrete dynamical system on the circle. So as you know, this kind of also is kind of a behavior of the PDE. Okay. And let me say that, okay, this is very hard to make sense of. We don't really know what converge means because, you know, a cascade of, you know, a kind of cascade of such bounces is not itself really an orbit. But let's just say that there are partial progress due to Ringstrom. This is 2001, and then Beguin and Dutier. And this is just for the ODE problem. So this is 23. Good. So that's all I'm going to say about the ODEs. Any questions so far? Okay, very good. So what Ringstrom showed is that, so if you really consider just the union of these heteroclinic orbits, so in the Bianchi 9 case, so in one of these cases, he showed that acts as an attractor for the ODE. Okay. What these guys showed is that there is, say, some positive measure set of initial data for which you really can show this in some quantitative sense. Okay. Again, I don't know exactly what that means, but roughly, yeah. Okay. Very good. Okay, good. So now I'm done talking about ODEs. Let's talk about the BKL proposal. Okay, so this was really over a series of papers. So let me say Kalatnikov and Lifshitz, that's 63. BKL, which is the main one, 71. Also in 82. And okay, lots more. Okay, these guys and other people wrote a lot of papers on this subject. And what they really want to say is three things. So this comes in really three parts. And the first part is that kind of general, or maybe let me say generic, let's put this in quotation marks, singularities are locally modeled by spatially homogeneous solutions. And I'll say a lot more words about what this means later. But okay, just to be a little clear. So let me say, if I think I have a singularity at t equals 0, okay, then the idea is that if I take a point on the singularity and I draw, say, some kind of region ahead of it, then in this region ahead of it, I expect this to look like model 1 or 2. Okay. Now I'll say more about what that means quantitatively later. Okay. Okay. Secondly, I want to. They say that. So even okay. So really, I said 1 or 2 over there. So I want to say that typically this homogeneous solution will exhibit these bounces. Well, will exhibit kind of a kind of funny cascade of things. Okay, so let me just say exhibit bounces or chaotic behavior. Okay, and finally, and this is really not a topic I'm going to discuss, is that somehow if you decide to include matter into the Einstein equations, then it doesn't really affect what happens near the singularity. So this is colloquially sometimes referred to as the fact that matter doesn't matter. Okay. Okay. I will say that there is exceptions to this. And this is mainly either the stiff fluid. So that's a perfect fluid with the kind of equation of state that the pressure is equal to the density, or the scalar field. Okay. But I think probably both speakers in the afternoon will discuss this, so I won't really talk about the influence of matter much in the rest of my talk. Okay. So okay, so I'm gonna really, I think the important thing, at least in my talk, is to really discuss one. What does one mean? Okay, so let's go back to that. Okay. So let me say the essential, or one essential difficulty, let's say, is showing this first thing. that somehow we're allowed to reduce to we're allowed to reduce the Einstein equations to something spatially homogeneous, which really means I'm allowed to reduce the Einstein equations to a system of ODEs. Okay. So in modern language, at least in the mathematical community, this is often known as let me write this out once. So asymptotically velocity term dominated, or ABTD behavior. Okay, so let me write down a definition, which is, again, not going to be completely precise. So what we'll do is we'll say the Einstein equations in a suitable formulation or a suitable gauge will exhibit ABTD behavior near the singularity, near a singularity, if kind of any dx derivative terms in the PDE. Okay, so when I say we say Einstein vacuum equations in a suitable gauge, that means I write it as a suitable system of PDEs. So if these dx derivative terms in the PDE can be, how do I want to say this? Let me say are kind of in some sense ignorable as t goes to 0. So something like they're small, and in fact, actually, if we have to do any integration, then we can ignore the rest as error. Good. So let me actually already make a comment. So I did put the word generic here, and maybe BKL didn't do that. But I will note that it is important, because if we really believe in something like this does exclude some things. So in particular, ABTD definitely excludes, let me say, non-trivial self-similar singularities. So in a self-similar situation, we'd really expect dx and dt to have exactly the same kind of size, okay? And in particular, this doesn't include things constructed by, say, Christodoulou, e.g. Christodoulou, the Einstein scalar field, or I guess the numerical construction of Choptuik, or the work in vacuum by Rodniansky, and I think your name is going to not appear on the board for me. Let me write SR. Okay, so we do have to be wary of those, but for the rest of this talk, I'm not going to be wary of these things. Okay. That's why I have, in some sense, it's trivial because I agree. Yes. Okay. So I'll just give one example of a gauge where we can really kind of think of this more fluently. E.g., if we take kind of an ADM type decomposition, so this is where we write the metric as, say, minus dt squared plus the Riemannian part. So this is with unit lapse and 0 shift. Okay. Then you can kind of schematically write Einstein vacuum equations as the following system of equations. So we know that the time derivative of the Riemannian part is the second fundamental form. Okay, I'm missing constants maybe. And okay, in this ADM formalism, the time derivative of k looks something like k squared plus the Ricci tensor of h. this is the three-dimensional Ricci tensor. And okay, if we just remember what that looks like, this is about something that looks like k squared plus. So this looks like, if you think about this in terms of Christoffel symbols, this is kind of the x derivative of a Christoffel symbol plus Christoffel symbol squared. Yep. Good. So we don't see a lot yet. Let me also, because I wrote down the Christoffel symbol, let me also write down the time derivative of that. So this looks something like the covariant derivative with respect to h of k. And that's what happens basically if you look at this equation. And remember that, okay, this also looks like an x derivative of k plus Christoffel symbol times k. Okay. Good. Does this roughly make sense? Okay, so this isn't that good yet, but what I'll notice here is we have an essential thing that says dtk equals k squared, okay? And that is really what drives blow up. So let me say that, so the Riccati term, dtk equals k squared, drives the blow up. And in fact, we really see blow up at the rate kind of 1 over t. Okay, so it's kind of, so what we're going to do is assuming the singularity is at t equals 0. So if t equals 0 is singularity. Oh, sorry, maybe I should switchboard. Okay, so the idea is that if t equals 0 is the singularity, it's kind of natural to rescale. It's to say k hat is equal to tk, and let me say gamma hat is equal to t gamma. And okay, let me just write down the system of equations you really will want to write down is something like tdt of k hat and tdt of gamma hat. And what you'll see on the right-hand side is, I think I've multiplied everything by t squared here, so we should have something like t dx gamma hat plus gamma hat squared. And then maybe here I have something that schematically looks like gamma hat plus gamma hat. Something like this. And basically what AVTD means, AVTD here means that we can, that these terms, the TDX gamma hat and TDX k hat are, say, uniformly small and maybe say integrable in T as T goes to 0. And it really means that I can ignore these two terms from the equation. I don't know why I put them here and here. And then really the rest of this really looks like an ODE, okay? And then let me just say the remaining part looks like an ODE. Okay. So, let me now state some results. So I'm not going to use this gauge, and in fact, from this point onwards, I'm going to be not talking about the 3+1 Einstein equations. In fact, there'll be plenty of that this afternoon, I think. So what I'll state. So this is from last year. Is that there exists a large class of Gaudi symmetric. I'll explain what that is later. Which exhibit AVTD behavior. But I want to say more than that. I want to say that they exhibit AVTD behavior even in the presence, even let's say if the resulting ODE exhibits something nonlinear. Okay, so in particular, let me say exhibits one bounce. So one kind of heteroclinic orbit connecting fixed points. Okay. Okay. So let me make some remarks. In the case of Gaudy symmetry, so in Gaudy symmetry, it turns out that some of the unstable, let's say some of the unstable orbits directions in the ODE picture are eliminated. So in particular, we don't have any chaotic behavior. Okay, so no. What else do I want to say? Maybe I'll state this theorem later, but maybe, so Ringstrom in 2008 actually already showed that kind of near each point on singularity, the spacetime does approach some kind of Kasner metric. Maybe I hopefully still have a diagram here. So if this is the singularity in a Gaudy symmetric spacetime, then in some region like this, we do approach some Kasner. And okay, this was kind of crucial for him showing the strong cosmic censorship conjecture in this class. Okay. So okay. So without further ado, let me write down what Gaudy means. Okay, so let me say a spacetime is Gaudy symmetric if let's say M is equal, let me just write this, and positive reals cross, let me just say R cubed. So X, Y, Z. And okay, the metric, this is slightly complicated, but bear with me. This is the form of the metric where P, lambda, Q are functions of T and X. So here, Y kind of d by dy, d by dz are killing fields. Okay. Then, okay, let me write down the Einstein vacuum equations. They reduce to the following. So we have the following T dt. P minus so we have this equation for P. We have another similar looking wave equation for Q, which I'm not going to write down. And then we have also two equations for lambda. So T dt, lambda, T dx, lambda equals stuff. Okay, maybe I should write down the right-hand side here. So this is minus 2 T dt. Okay. Let me just say that these two equations, you see they only see P and Q, whereas, okay, this might see P and Q on the right-hand side, but what's important is we can kind of solve these two equations completely independently. So let me just ignore these two equations for the rest of the talk. They can be thought of as constraints. Okay. So d by dy and d by dz are killing. Yeah. So typically x, y, and z would be periodic, but it doesn't really matter so much. Okay. Let me just say this in words. So you could be worried about, so this is actually very nice, right? What we've done is we've reduced the whole problem, the Einstein equations, to actually a semi-linear system of PDEs for P and Q. And in fact, these have a lot of structure. And in fact, you get global existence, meaning I have existence in the whole interval of t from 0 to positive infinity kind of for free. Okay, so I don't have to worry about that. So what I'm going to be interested in instead is kind of understanding asymptotic behavior, especially as t goes to 0. So what happens with t small? What does that have to do with BKL? Okay. So what I'm going to be doing is I'll derive ABTD for an increasingly complex Gaudi spacetime. Okay, great. So the kind of easy case is something called polarized Gaudi. So this is where Q is equal to 0. And there actually we just have a linear equation, right? We have a single linear equation, which is T dt P, so T dt squared P minus T dx squared P. 0. And okay, here's kind of a theorem, which is due to crucial Heisenberg-Moncrief. Which is that we expect, well, there exist functions, I'll call them v of x and psi of x, such that let me just say p is equal to v of x log t plus psi of x, plus kind of little overlap as t goes to 0. And what that really means is that I can throw away this term, right, and just integrate this equation up twice. And that's exactly why I get an expression like this. Okay, so let me give you a proof of that theorem. Proof. Okay, so we have a wave equation. It's very natural to do some kind of energy estimate. So if you have an energy, which I'll call E0, T, which is kind of the x integral of the following thing. So T dt P squared plus T d theta P squared dx. Then what you can actually check is that d by dt of E0 is positive. Okay, so that means this energy remains bounded as t goes to 0. Okay, so okay. But we have a lot more, right? I mean, this linear equation I wrote over there actually commutes very nicely with d by dx. Okay, so what I want to say is commuting by d by dx, we can actually commute as many times as we want. So ek t, which is the same thing, but with kind of, let's say, up to k derivatives of p. Has the same monotonicity, right? Also has EKT bounded. Okay. And then we're done because we can use Sobolev. So that means by Sobolev, we actually know that, say, expressions of the form t dt dx to any order, really. This is bounded in L infinity. And in particular, we have that kind of dx squared p. This is bounded by, say, log t. Okay. So that enters exactly here, right? And in fact, it enters with an extra t squared. Which clearly goes to 0 as t goes to 0. Okay. And that's basically how the proof goes. Okay. Good. So now okay, now let's talk about what I'll call monotonic Gaudi spacetimes. Okay, so at this point, we're going to go back to the full equations that are over there. And what it's actually going to be useful to do, so this is not how I did it in the paper, but it'll be useful to reinterpret the equations for P and Q as a symmetric hyperbolic system. So in particular, okay, let me make some definitions. So alpha will be minus t dtp. Beta is equal to minus t dxp. Gamma will be e to the p t dtq, and delta will be e to the p t dxq. And okay, what you can really see is that you can think of alpha and gamma here as kind of k, as the second fundamental form, because it's kind of a time derivative of the metric. So kind of k is equal to alpha and gamma. And similarly, the kind of Christoffel symbols are the other two. Okay. And then it turns out we can write down a big symmetric hyperbolic system. So t dt alpha let me write here t dx beta plus, and then it doesn't matter so much what the terms are, other than a few of them. Gamma. Okay, very good. Okay, so now, okay, there is again a natural energy. So, so let me say e to the k t will just be something like you have k derivatives of alpha and so on. And okay, what it turns out you'll be able to show is that can show that if you take the following, you can do the following energy estimate. Okay, and what you'll be able to show is that this is actually kind of bounded. Maybe I should put this in absolute values by, say, like the L infinity norm of, this is kind of morally true, that the L infinity norm of alpha times EKT times some constant. Okay. So it's not as clean as this case where we have monotonicity, but what you have is you have kind of a growth bound on energy. So EKT is bounded by something like t to the minus c times. Okay. And the idea is that the goal will be, okay, so I didn't explain what monotonic regime is yet. So, so in the monotonic case, so alpha is strictly between 0 and 1. Okay. And if alpha is strictly between 0 and 1, you'll see that the ODE thing, so if you ignore these guys, okay, then what you do is you'll see that you expect all of beta, gamma, and delta to go to 0. Okay. And why is that? Right, you see TDT beta equals beta, so that kind of goes to 0 as t, okay? And okay, crucially, okay, we ignore those terms now, and if you see these terms, alpha being strictly between 0 and 1 is exactly what you need to make these terms also go to 0, okay? And then, okay, again, if we expect this monotonic case, then this thing is also t, something like, this becomes t to the minus c, okay? And this is kind of good enough, right? And why is it good enough is because this C doesn't depend on K. Okay. And what you can still do is you can use Sobolev embedding, or maybe something a bit stronger. Let me say Sobolev interpolation to show, for example, that dx of alpha. Okay, so what we're doing is we're interpolating between k derivatives here and 0 derivatives if we expect this kind of bound to be something like t to the minus c over k. Okay, and then what does that mean? That means that so t dx of alpha is maybe bounded by t to the 1 minus c over k, and it still goes to 0. Okay, and this is as long as k, for k large. Okay. So in this case, actually, we haven't done any bounces yet. We've ignored all these terms, and everything else, beta, gamma, delta, they behave very nicely. Yeah. Yeah.
Is there something with the C about K?
Yes. Yeah. No. It's more like it's just there's one top order term the top order term only ever sees alpha. It doesn't see like derivatives or anything. Sure. Yeah. Yeah. I can explain. I mean, it's maybe it's more the definition of my energy is a bit off, but yeah. Okay. So in maybe 1 minute, yeah, okay. I think in reality, like maybe this also has to contain an alpha squared. Sorry, dx. Well, okay. Maybe I'll okay. Okay. So let me do the more complicated case where we might expect bounces. So here I'm gonna instead here I'm gonna kind of assume, okay, assume really, okay, maybe I'll write it properly. So I'm gonna bootstrap, not that alpha is between 0 and 1, but between 0 and 2. Okay. And if I still believe those equations, I still have and ignore kind of beta and gamma. So I'm left with the following thing. T dt alpha, T dt delta equals maybe delta squared here, and then 1 minus alpha delta here, and then I have a TDX term. Okay. So now ignoring I really don't have time. Can I run over 5 minutes? Okay. Okay. So ignoring the TDX star. Okay. What I have is I have something like TDT of alpha delta is equal to delta squared 1 minus alpha times delta. And what this is, it's a two-dimensional dynamical system, and it has the following kind of phase portrait. So this is the delta axis, alpha delta. So you'll see that the fixed points here are exactly where delta is equal to 0. So this is actually, it's just this kind of vertical axis. Really, you can think of that being morally the same as the Kasner circle. It's just a one-parameter family. Okay, but in this family, you'll see that you'll see that if you have points up here, they have one unstable direction, and what it'll do is it shoots again a heteroclinic orbit or a bounce, and it will connect down there somewhere. Okay, and okay, if you actually compute, this connects alpha here to 2 minus alpha there. So it's actually exactly a semicircle around the point 1, 0 here. Okay, and then similarly on the other side. Okay. Very good. So, okay, we have this picture, and this transition here is exactly what I think of as a bounce. And it's certainly going to exist. If I just assume alpha is between 0 and 2, then really some of these transitions I'm going to see them. Okay. Okay, so the next question is, how can I estimate these? Okay. So in the best case scenario, even if I forget about these terms and I just have this ODE, so in the best case scenario, what I have is that T by TDT of dx alpha delta is what I can do is I can just commute the ODE with d by dx. Okay, and what I see is I'll see, maybe I should write dx alpha this. What I'll get is just use the chain rule naturally. Maybe I get something like 0 to delta minus delta 1. So what I have is just like a matrix here, dx alpha, dx delta. And okay, what I really want to say is that this is actually a linear ODE in these derivatives. Okay. Okay, so I want to say linear ODE for exactly the dx alpha, dx delta. And in particular, I can see, well, it kind of suggests, let's say, that if I look at the size of dx alpha and dx delta, that it grows as some power of t, where here negative sigma is, say, the minimum eigenvalue of m. Okay, because here I have a matrix. I can do some kind of matrix exponential type thing. Okay, in reality, you can't quite do that because m is time dependent, but I'm not going to say much about that. Okay. And let me just say that this is exactly why. So to get sigma less than 1, this is why we need alpha strictly between 0 and 2. Because if alpha was greater than 2, here we would get a much more negative number than negative 1, and that seems bad. So in this case, we expect, what do I want to say? We expect t dx star, whatever that is, to grow exactly as t to the 1 minus sigma, so still fine. So, okay, this doesn't quite work out, right? Because of course there's another term here that has second derivatives, okay? And okay, as always, in order to deal with that, to deal with the kind of top order term or like loss of derivative, Okay, let me just say, like, okay, let's now say that the energy estimate, we use another energy estimate. So what the energy estimate gives now is something slightly worse than before. And okay, I can maybe explain where some of these terms come from. We do the same thing. Okay, so let me maybe write out terms now. So because we have this delta on the right-hand side, we'll have terms that look like the following. So 2 delta dx. Okay. So that's because we can commute this delta kind of k times. Yeah. But okay, we might have to worry about something else, which is that even there's even terms that maybe look like dx delta, and then we have dx k minus 1 times. Okay. Okay, this is maybe the most technical step. So this term here, just as in this case, in the case B, I'm really bounding this by constant times maybe delta in L infinity times the k energy. Yeah. Okay. So okay, maybe that explains why you get alpha. Like in the other, okay, there's also a term that happens when you hit the final term, I guess. Okay. Okay, but how about this term? Well, here, okay, forget about this. But if we see this term, we might have a problem, right? Because this term here, we only have a bound of minus sigma, right? So here, this is bounded by t to the minus sigma instead. Okay, so this is, let me just ignore this, basically. But the reason we're still okay is because maybe instead of having k here, we can really write k minus 1 instead. This is one less derivative. Okay. Good. And what that means is at the end of the day, you will still get something like ek t is bounded by, so just as before, we have t to the minus c. Okay. But actually, we get a little bit worse every time. So maybe every derivative we take, we lose a sigma. Okay. Maybe there should be a 2 here in order. Well, who knows? But okay. Yeah. Maybe I should write square. Okay. Okay. Maybe let me just say that this is still enough. And what I mean by that is if you do the interpolation, you will still see that you lose the sigma, but actually losing the sigma is correct because in some sense, every time you take a dx, you're happy to lose exactly t to the minus sigma, and that's fine. Okay, that bit at the end maybe was a bit technical, but let me finish that.